Today we will discuss about a very interesting, rather very important topic which is named as nuclear force. At first, you may observe that nucleons which are consist of proton and neutron. Now, sorry, proton and neutron. Now, out of which proton is charged particle, whereas neutron is chargeless. So, how can these charged particle may accumulated at a certain region in space without repulsion? This was a very burning question in that day. So, scientists observed that there exists some another force which is beyond our knowledge. Unlike gravitational force, at first it was think that gravitational force may exist, but gravitational force is very weak. So this is not possible in that certain region of nucleus. So gravitational force is not present in between the nucleons. So the force that exists between these nucleons is unlike gravitational force and Coulombic force, because Coulombic force is charge dependent force and it is repulsive in character for the same charge configuration which is present in the nucleus, because protons are positively charged, so there will be a strong repulsion if Coulomb force exists between them. So there must exist some another kind of force which is very strong in nature and independent of charge. Okay, so this new force was named as nuclear force because it is beyond our knowledge. I am saying this at this beginning of the nuclear physics study. Okay, so this was a nuclear force which exists between the nucleons. Now the scientists were very much eager to know the basic information about the nuclear force, how it originates, what is the range of the nuclear force. This was a very interesting topics. These were the very interesting burning questions in that day. So scientists performed very experiment and gave many models regarding this nuclear force, out of which a very successful model was given by Yukawa. We will discuss this Yukawa's theory, which is Meson theory, Meson exchange theory. Meson exchange theory. I will be there after some time. Let us first discuss. To study the nuclear force, we have to consider the simplest case for which there is present only two nucleons and one electron out of the nucleus surrounding it. Okay, so the simplest case was considered for deuteron nucleus, which consists of one proton and one neutron. Why hydrogen was not considered? Because hydrogen consists only one proton and one electron, which is revolving around the nucleus. Okay, so deuteron nucleus was assumed to considered for the study of the nuclear force and the nature of the nuclear force. Now, for the study of the nuclear force for deuteron atom, the potential that was assumed was finite square well. That is, uh, it it has been shown already in quantum mechanics lecture that finite square well potential exists. That in certain space there is some potential, say V naught, and out of that space the potential is zero. So here the potential was considered to be negative this up to a certain region, say B, and beyond that region the potential was zero. Now as the nucleons are bounded to a system, the potential was taken to be the negative, that is it is negative of V naught and outside it it is zero. So we can, it was assumed that potential was radial function as was assumed in case of hydrogen atom problem. So we are very much familiar with this. So here was assumed that uh, minus V naught up to R less than equals some b, and it was assumed 0 at the region greater than b. Okay. Okay, so let's go beyond it. So let's first study the Schrodinger equation regarding this. Let me write the time independent Schrodinger equation. Grad square psi plus 2m upon h line square e minus v naught, sorry, okay, e minus v into psi is equal to some 0. Just a minute. Okay, so named it equation 1. Name it equation 1. Now this is a spherically symmetric case, as because nucleus was first assumed to be spherical in shape, and since it was spherical in shape and Vr is also radial function, V also is a radial function of potential, so the grad square can be taken in spherical polar coordinate. It has been already shown in hydrogen problem lecture, that is grad square can be compared to 1 by r square del r of r square del r of psi, which will be written later. Okay, del r square del r plus 1 by r square sine theta del theta sine theta del theta plus 1, sorry, 1 by r square sine square theta del 2 del phi 2. If we put the expression of grad square in equation 1, we will obtain some simple expression. Let me write 1 by r square del r square del psi del r plus 1 by r square sine theta del theta sine theta del psi del theta plus 1 by r square sine square theta del 2 psi del phi 2 plus 2m upon h line square. Let me write this below. Okay, plus 2m upon h line square e minus v. Let us first write the general expression, that is v r theta phi. We will then transfer it to only vr. Okay, let me write here vr psi is equal to 0. Now this is a two body problem in which we consider a proton and neutron, and in the hydrogen atom lecture we have seen that these two body problem can be treated for the variable of separation method, that as a composed of the free particle with respect to the center of mass system and a particle of reduced mass of the two particles with respect to the relative coordinate, to make it variable separable. So for that case I am not going into detail, and must separate it with variable separation. This is composed of psi. This may be treated as capital psi. All the psi's are capital psi here, and in this line we can treat it small r, small psi r, and function say y, uh, theta and phi. Okay, so this was the radial part and this is the azimuthal part. So if we put here, then we will obtain some variable separation method, and this results some 1 by r square del r. Here y is constant, r square del psi del r plus here psi is constant, and here will be the total derivative. Psi 1 by This is equation number 3. If we divide the whole equation by y into psi, then we will obtain the one part which is solely dependent on r and another part which is solely dependent on y. So let me jump some steps so that the radial part become 1 by r square, some dr of r square d psi dr divided by some dr plus 2m by h line square e minus vr minus L into L plus 1 by 2m r square into some h line square psi r is equals 0. This was the equation number 4. Now why I am jumping some steps, because these steps are very well known to you, as because I have already discussed it in my hydrogen atom lecture. So if you do not understand this, please go to that lecture and make it understand. If I am going into detail in this calculation, then it will be very long discussion. I am not at all in a position to discuss it very elaborately, as because I have already done it. So let's go further. Why L into L plus 1 was taken? Because we have considered some constant lambda which was equal to some L into L plus 1. I have already discussed it for the property of legendary polynomial, associated legendary polynomial. So I am not going into detail it. So let's go further. So this was our familiar radial equation. Okay. So this was our familiar radial equation. Now L is here the orbital angular momentum quantum number. We know it very well. Sorry, orbital angular momentum quantum number. Just similar to the hydrogen atom problem. Now, for ground state, if we consider the ground state of deuteron, then L will be 0. If L will be 0, then orbital angular momentum must be 0, because we know that orbital angular momentum is related to L into L plus 1 into H line. So if L is 0, then L is also 0, capital L is also 0. So for ground state of deuteron, L is taken to be 0, and if we put this value in equation number 4, then we will obtain that 1 by r square d dr of r square d psi dr. Okay, write this 2m by h line square e minus vr into psi r is 0. Why? Because L is 0, so this term will be vanished. This is the equation number 5. So this is named as a state of deuteron, as because L is 0 here, you know, as because L is 0. Okay, so let's go further. So this is nothing but the a state of deuteron, and it is assumed to be spherically symmetric. Why? Because this is independent of theta and phi, and because there is no any orbital angular momentum at all. So we know very well that in S orbital is spherical in shape. So the S state of deuteron is assumed to be spherically symmetric. So our calculation that the potential is taken only as a function of r is very correct. So now the psi r is function of r. It can also be taken as ur by r to make the equation 5 very simple. Why I have considered this? Only because to modify the equation 5 into a simple equation. Now let's calculate the d psi dr. What we will see that this will equal to some 1 by r du dr minus a 1 by r square ur. Okay, so if we consider another derivative with respect to r, then it will be nothing but minus of 1 by r square d2u dr2. Okay, let's first write. Okay, uh, just a minute. At first it is constant, so 1 by r d2u dr2 minus 1 by r square du dr minus 2, so plus 2 mm, by r cube u. Okay, uh, minus 1 by r square du dr, so 1 by r d2u dr2 minus 2 by r square du dr plus 2 by r cube u. So if we obtain r square d2 psi dr2, then we will see that this is nothing but r d2u dr2 minus 2 du dr plus 2 by r u. So name it equation number, just a minute, 5, this is 6, 7, and this is 8. Okay, so let's go further. So now if we take from here r squared d psi dr, then we will obtain r du dr minus u. Let us box it, as we will use this in further calculation. Now here r square d psi dr is present, so we will place the value of this here, and so place this value, um, 1 by r square. Okay, so mm, okay, let's further calculate ddr of r square d psi dr. So from it calculate ddr of r square d psi dr. So r d2u dr2 plus du dr minus du dr. So this will get vanished and simply becomes d2u dr2. Placed it in the value of equation 5 here. So 1 by r square into r d2u dr2, okay, plus 2m by h line square e minus vr into psi r is taken as u by r, no? So u by r, just a minute, okay, u by r is equal 0. So if we multiply the equation by r, then we will obtain d2u dr2 plus 2m upon each line square e minus vr into u is equal 0. This is a very simple equation to calculate further. Named it equation 9. Okay. Now the actual form of the potential have to be considered. What we consider that VR is equal some minus V naught, where R less than equal V, R less than equal B, and 0 beyond B. So we have to divide it into two regions, region 1 and region 2. So for again the ground state energy, ground state total energy will be negative since it is bound state case, you know what, and equal to the B, which is the binding energy of the nucleon. Okay, so if all this value is incorporated in equation 9, then in region 1, let me write here, in region 1 this becomes some d2u dr2 plus 2m upon h line square. E is taken as minus of b because E is negative, so E is taken as minus of b, and VR is minus of V naught, so minus minus becomes plus, so V naught, and E becomes minus, so V naught minus B. This is 0 where in R less than equal B, named it as 10. Okay, and in region 2, d2u, the potential is 0 and this is some minus of V, so d2u dr2 plus 2m upon h line square minus of B into u is equals 0. Now I have forgotten to take into account a very important concept. What is this? Let me highlight it. What is this? This is the mass of a single particle, but we are in a position to deal with some two particle system which must be reduced to one body system. Okay, so we have to take the reduced mass of these two particles, proton and neutron. So if since we know that the proton has a mass 1836 times that of the electron and the neutron has a mass 1839 times that of the electron, so these two masses can be nearly taken to be comparable. Let us say MP nearly equal to some Mn equal to some M. So the reduced mass becomes capital M, MP Mn divided by some MP plus Mn, which is nothing but M square divided by 2M. So if we done simplification on it, then we will get M is equal nothing but M by 2. So these should be reduced to capital M. Mm, okay. Okay. Okay, here I have done the reduced mass already, na? Here the reduced mass, because if we do not consider the reduced mass, then we will not obtain at all the separation of variable. So here the mass which is taken into is reduced mass, and this was the actual mass. So this is the actual mass. So okay, I have done it in opposite, na? Okay, please give me some time. I have to modify it. So the um, reduced mass becomes capital M square by 2M So capital M will be 2m. So this is equal to some 2m and this is also equal to some. Okay, here m is the actual mass which is taken to be comparable to the mass of proton and mass of neutron. Okay, so let us now go further calculation. The general solution can be taken. We have solved many equations like this in quantum mechanics. So we have to use the results obtained from this equation, from the solution of these equations. So the general solutions of in region 1 can be taken as u as a function of r a1 sin kr plus b1 cos kr. What is k here? K is nothing but some m upon h line square. K square is nothing but m upon h line square v naught minus b. Okay, this is the equation number uh, 11 and this is the equation number 12 for region r less than equal to b. Okay, and in region 2 ur can be taken to be a2 e to the power alpha r plus b2 e to the power minus alpha r for r greater than b, r greater than b. This is the equation number 13 where alpha is taken to be equal to some m upon h line square b. Okay, now we have to apply some boundary condition. Boundary conditions, what are these? U is 0 where r tends to 0, as because we have considered the model that this. So at r tends to 0, the u must be, the wave function should vanish, and at r tends to infinite the wave function should vanish, because here we cannot take the minus infinity sign. Here the r tends to 0 is the left hand limit and r tends to infinity is the right hand limit, so the wave function should vanish at the boundary of the two region. So applying these boundary conditions in equation 12 and 13 we will obtain some value. So applying these boundary conditions in equation 12 and 13 we will obtain that u in region 1 a1 sin kr. Why? Because u is 0 at r equal to 0, so b1 is 0, so this becomes this, and u becomes at r tends to infinity, this term goes over 0. Okay, and this term becomes infinity, so we have to write only b2 e to the power minus alpha r. We also know from normalization condition this is possible only. So these are the final expressions of the wave functions obtained here. Okay, so again from normalization condition we can calculate the a1 and b2. So I am not going into further detail of these two calculations, as because we are not interested at all the constant, what is the nature of the normalization constant. We are only interested to the nature of the wave function obtained here. So at the boundary, that is at r is equal b, the two wave functions should be equal. So at r is equal b, sine kb is equal some b2 minus alpha b. Okay, and this is u1b is equal u2b. If we name it u1 and u2, then this. Similarly, the first order derivative should also be continuous. So applying this first order derivative, we get okay, k a1 cos kb is equal to minus b2 alpha e to the power minus alpha b. Name it equation 14 and 15. Now 14 divided by 15 implies a1 cancels out, so k cot kb becomes minus alpha e to the power minus alpha b. So cot kb becomes minus of alpha by k. Just a minute, e to the power alpha b cancels out, so this is not possible here. So the final expression is this. Okay, so if we draw the wave function completely, let me take the coordinate axis. Okay, the potential was taken like this. This was the position R and this is R. If we plot the function UR here, then we will notice that the wave function becomes this, since it is continuous, and then exponential decay occurs. So more or less this. So this is the ground state of bound ground state of 3s. Why I have write this 3s deuteron. L is equal 0 is considered for ground state, so for L equal to 0 this becomes S, and the the multiplicity for since it is its spin is half, so its multiplicity becomes 2. Just a minute, there is a reason, but it cannot be understand here. I will discuss later the reason of writing this, so please have your patience and see at the next topic. From the above calculation of the ground state of Deuteron, the very striking features are coming out. What are these? Ground state properties of Deuteron. Ground state properties of deuteron. First property is its binding energy is very low, of the order of 2.23 mega electron volt. As because the average binding energy is 8 mega electron volt, with that respect this binding energy is very low. Okay, the next one is the total angular momentum of deuteron is observed to be 1, and the orbital angular momentum is observed to be 0, and we know that L plus S is equal I. Total angular momentum is taken to be as I, so L plus S is equal I. Please take the vector sign. So S again we know that S1 is half for proton and S2 is also half for neutron. So if we take the spin SS coupling, then this will have some value 0 and 1. So if we take 0, L is already 0. So if we take S equal to 0 here, so the total angular momentum must be 0. But this is not the actual case. Total angular momentum is 1. So S is 0 is not taken. S is 1 is taken only. S is equal 1. Since S is equal 1, the multiplicity must be 2S plus 1. That is 2 into 1 plus 1, which is nothing but 3. This. Okay. Now the third striking feature that was observed, that the proton has magnetic moment equal to 2.792 nuclear magneton, and neutron has a magnetic moment of minus 1.913 nuclear magneton, sorry, beta n. So the actual magnetic moment of the deuteron should be mu p plus mu n, which is nothing but sum equal to 0.879 beta n nuclear magneton. But the observed magnetic moment of deuteron was observed, this is calculated one, and observed value is 0.857 beta n. Even the most precisional measurement have shown this. So we have seen that there is some difference between the observed and calculated value. This difference has no any explanation at that time. Why this difference created is not cannot be explained at that time. The fourth striking feature was observed that the deuteron has the quadruple moment, very light color. Deuteron has some quadruple moment 2.82 into 10 to the power minus 27 centimeter square. This is very small quantity, but not at all zero. If we consider the deuteron nucleus to be spherically symmetric, then the quadruple moment must be 0. As we have shown in nuclear physics lecture 1, that the total electrical quadruple moment is 0 for the spherical configuration. So for deuteron nucleus there should be the quadruple moment 0, but the observed or calculated the observed value from different experiment of quadruple moment of deuteron is observed this, which is although very small but not at all 0. So there is also a huge discrepancy of the model. So whatever we taken into account that V is a function of R only, that is spherically symmetric, is not truly possible. It may be partially possible but not truly possible. We will see in later that what occurs there. Now my aim is to try to give the explanation regarding these discrepancies. So put the heading explanation of magnetic dipole moment and electric quadrupole moment. Electric quadrupole moment. So whatever we observe that the magnetic dipole moment is there is a difference in observed and calculated magnetic dipole moment. This and uh, wait a minute. Okay. So whatever we observe that there is a difference between the observed and calculated magnetic dipole moment and the quadrupole moment, which is non-zero quadrupole moment, which is the cause of our headache. So we are going to explain the reason behind it, behind these discrepancies. So whatever we take that the V, the potential as a function of R, because of the spherically symmetric configuration of the Deuteron nucleus, and for ground state we take that L is equal 0. So A state of Deuteron was taken, and for A state of Deuteron this was taken to be spherical, because similarly we can know in a similar manner that S orbital is spherical in shape. So we can compare this, but these are different, not same. So we can compare this that the S state of the deuteron is spherical in shape. So there should not be the solely dependent on the L equal to 0. The wave function of ground state should not solely dependent on S state, that is psi is equals psi 1s. It cannot be solely dependent on psi 1s. So we can take these as a combination of two different orbital angular momentum quantum number, L equal to 0 or L equal to 0 and either L equal to 1, 2, because we know that total orbital angular momentum is 1, and it is nothing but the sum over L and S. So L should have the value 0, 1, 2, because it is 1 and it is also 1. So L should have the values 0, 1, 2. But from the conservation of parity, we note that psi cannot be taken as a combination of mixture of even and odd parities. If we take the value of 1, then the parity will be odd, and if we take the value of 0 and 2, then the parity will be even. So we can take the combination as 0 and 2, but not 0 and 1. So we can write that psi 1s plus psi 1d. Why is 1 is for ground state, okay, because we know it very well from the shell model. Now there should be some normalization constant, this is A0 and this is A2, okay. The square of these gives the contribution by which psi 1s is present in the system and psi 1d is present. So this gives the contribution or probability of psi 1s, contribution of psi 1s on psi, and A2 square gives the contribution of psi 1d. It has been observed experimentally that the value of this is 0.96, that is 96% probability to get the deuteron nucleon to be in psi 1 state, and 0.4, this value is 0.4, so 4% probability that of psi 1d. Okay, so there should be some contribution of the orbital angular momentum as well, along with the spin angular momentum, for the explanation of magnetic dipole moment and the electric quadrupole moment. For that case only the quadrupole moment will be non-zero. And why 1 is not taken? Because of conservation of parity. So this was the explanation regarding the magnetic dipole moment and electric quadrupole moment discrepancies. Now, if there is present some contribution regarding orbital angular momentum L, then there should be some torque acting on the system, which is nothing but dl dt. You know it very well from the classical mechanics as well as quantum mechanics. Now torque can also be written as, the magnitude of torque can also be written as magnitude of r cross f, which can be taken to be some rf simply, and which is also taken to be some minus of del v del theta. So from this, if v is dependent on r only, then these values should be 0 and there will be no torque. If the no torque, then the no torque acting on the system, then the system will be conserve on orbital angular momentum. The rate of change of orbital angular momentum will be 0. Okay, for that case only L is equal constant, but L is not at all constant. This is a combination of 0 and 2. So torque should be non-zero. For that, del v del theta should be non-zero. For this case, v should also depend on theta as well, not at all only for r. V is also dependent on theta as well. So whatever we done in previous discussion, there was a small mistake. This was not mistake. The latter, the theory gets modified by the v, which is also a function of theta as well. Okay, this was the previous section was not the mistake. The previous section gets modified here. Okay, so v is a function of theta as well. Now the force associated with it is known as the tensor force, and the potential associated with this angular momentum is known as tensor potential. So the actual potential v becomes v central plus v tensorial. Now why the term tensor is applied here, I will give you explanation of it. Let us first now study that if we place two bar magnet, north pole and south pole, let's shade it. Okay, this is the north pole and this is the south pole. Okay, and another bar magnet is also taken, which is placed at parallel to each other. So there will be some repulsion between them. But if we placed these two bar magnet, which are placed like this configuration, and the line joining them is also parallel to their uh, orientation, then these will give rise to attraction, and this gives rise to repulsion in this configuration. Okay, similarly, if we take the deuteron nucleon, which has the spin like this and which has the spin like this, which is perpendicular to the line joining them, this gives rise to repulsion. And if the two nucleons which have the spin like this, and the line joining them is also parallel to their spin, gives the attraction configuration. So what conclusion have done here? Conclusion: the tensor force bears semblance to the force law between the two magnets in so far as their uh, in dependence on orientation is observed. So the tensor force must be dependent on their orientation of the spin, and it can be shown from the detailed calculation which is beyond our scope for discussion, that the tensor force Vt can be taken to be R into 2 into S dot R by R square, and S dot R square minus S dot S. So the force must be so the potential, which is the tensorial potential. Why this is termed as tensorial potential? Because it is the uh, non uh, symmetric, because it is the second rank tensor and tension and the product of uh, two scalar quantity. Okay, it is the scalar product of, sorry, uh, please give me some time. Acha. Okay, so it is the scalar product, means dot product. It is the scalar product scalar product these are vector quantity. So this is the scalar product of two second rank tensor so it is termed as tensorial potential, termed as tensor potential tensor potential tensor potential. Okay, now so this is the tensorial potential, and the tensorial force is related by this tensorial potential. Now the r square in the denominator is present only because to make the dimension a finite number, because this is a finite number, and okay, this is also for the conservation of dimension, the r square in the denominator is present, and this calculation is beyond our scope. This calculation is beyond our knowledge of BSc. In master degree we can calculate, and this is not known to me because I am a graduate student, and this is not known to me. So this calculation is dependent on the master degree. Okay, at the master degree you will study the detail of this calculation. Now the only conclusion here is that we have to know that the tensor force which originates from this gives the actual explanation regarding the non-zero quadrupole moment. Okay, Now let's move on. The nature of the nuclear force and different properties of the nuclear force. The nature of the nuclear force was first given, and the detailed model and satisfactory model of nuclear force was first given by Yukawa, scientist Yukawa's theory of exchange force. Exchange force. Now, what is this? This is very interesting. The term exchange force. In 1935, this model was given by scientist Yukawa. In 1935. Uh, are we know that what is the origin of Coulomb force? Coulomb force. Is it known to us? If not, then let me explain. According to electromagnetic theory, the charged particles are assumed to be surrounded by some field which is consists of photon particles. What I say, that the every charged particle is surrounded with some photon particles, and the force of attraction or repulsion with the same with the opposite or same charges gives rise to exchange of photon particles. Exchange of photon particles. Photon particles for electrostatic force of attraction and repulsion. Electrostatic or electric charges. Electric charges. The exchange of photon particles takes place. So, this is not an instantaneous phenomena. The charged particle, if a charged particle exerts a force of attraction on the oppositely charged particle, then there should be some exchange of photon particle which takes some time equal to the speed of light to cover the distance, okay, which must propagate along the speed of light c, which must have to propagate along the speed c, which is the speed of light in free space. So this is not an instantaneous phenomena, but this is not a very large time. There is a very short interval of time. So the Coulomb force originates from the exchange of photon particle. If a charged particle release some photon, then the other charged particle will absorb it, and if the other particle absorb it, and then other particle release it. So these absorption and release of photon particles gives rise to the Coulomb force. Similar model was given by Yukawa, and he considered some classical example of it, that is persons two persons who are playing basketball catch. Now, what he considered, that when one person, the two person, let us take on a movable object, say a boat on a river, then and two person are playing catch. Okay, so if one person release the ball to the other, then he will experience some backward momentum. When he release the ball, uh, then he will experience some backward momentum because the boat is movable. Similarly, the person who catches the ball will also experience a change in momentum in the backward direction. So there is a net change in momentum which takes place in opposite to each other. This gives rise to a force which is known to be the repulsive in nature. Repulsive in nature. So what he considered, that if two person playing the catch, then if he throws this ball, then he will experience a backward momentum change, and the person who receives the ball will experience the momentum change in the backward direction. So the resultant momentum will change like this way and this way, and this gives rise to the force of repulsion. But if the two person now throws a boomerang, suppose in this way, and this particle will receive this boomerang in this way, then when he release this boomerang, then he will shift to in this way, and when to catch the boomerang he will be in this way. So there the rate of the net change in momentum takes place in this direction, and these gives rise to the attraction attraction force. Now there should be some repulsion. Similar theory is applicable to the nuclear force. The nuclear force is repulsive in nature for some small region, because if the repulsive nature is not present, then the proton and neutron will be superimposed to each other, and the separation between them will vanish. If this will happen, then the nucleus will totally get collapsed, and the every nucleus will have the same size, but this is not observed experimentally. So there should be some repulsion, but the total whole nature of the force is attractive. Okay, there should be some repulsive in nature. If we plot them, then we will see that this gives a repulsive nature and this gives the attraction. So up to 0.5 mega electron volt or 0.8 mega electron volt, the force is repulsive in nature. If this was not present, then the total nucleus will get collapsed, and the nucleus, all the nucleus will have the same size, and the proton and neutron will superimpose to only a single point. But this is not possible actually. The nucleus has a definite volume, although very small, but has a definite volume, and the nuclear force ranges up to some Fermi order. We will see this. Now this picture is also illustrated here in detail. So what is shown here, when the person throws the ball like this way, he will experience the net change in momentum here, and the person who receives will experience the net change in momentum here. But when he throws this boomerang here, he will shift here, and if the person who receives will experience the momentum in here. So the rate of change of momentum, that is a net change in momentum, will be along this, and this gives rise to the attraction. Okay. So this is a very interesting and simple model regarding the nature of the nuclear force, which was first given by scientist Yukawa. Now he considered this exchange force to be the exchange of Meson particle, pi mesons, exchange of pi mesons. Like the electromagnetic theory, uh, the exchange of photon takes place. Here the exchange of pi mesons takes place. Now why pi mesons are chosen? Because pi mesons have some finite mass. Finite mass. Let us suppose this is m pi. So if a proton and a neutron be exchange some pi particle, then this will be treated as proton first transforms into some proton plus uh, and pi plus, sorry, uh, proton, let us suppose that proton gets transformed into another neutron and pi plus, and this is the neutron. So this proton gets transformed to this, and the neutron is present this pi will be received by this, and there will be n prime plus p prime. The neutron and proton, all the neutron and proton in same in character, but the prime denotes the position coordinate is changed. What position coordinate has p, different position coordinate will have p prime. So this proton gets transformed to this neutron, and this neutron gets transformed to this proton. So I use the prime to denote the difference between them. Okay. Similarly, a neutron may receive pi minus. Neutron may receive pi minus. So this is the neutron, and this pi minus will be absorbed by this, and this will become this. Okay. So this neutron gets transformed to this proton, and this proton gets transformed to this neutron. Again, neutron, neutron, this neutron uh, gets divided to this pi 0, and this neutron is present. So this neutron release pi 0 and this neutron receives pi 0. So this becomes two different neutron. The difference in what respect? The difference in coordinate respect. Okay. All the properties are same, but the coordinates are different. Position coordinates are different. Similarly, proton-proton transformation may also happen. This proton, this may release pi 0 and this may absorb pi 0 to become another proton and another proton. Okay. These are the different process involving the neutron-proton exchange force and exchange of these particle. Okay. Now you may ask me that if the proton release some pi 0, then there should be some decrease in mass. There should be some decrease in mass of the particle which release this Meson, which release this Meson, release the Meson particle. Correct. But experimentally it has been observed that there is no any decrease of mass. You may ask that this is the conservation, why this is the violation of energy. So the energy is not conserved because the mass is not constant. Here the mass should decrease. If mass should decrease, then it will get transformed into energy. So the energy conservation gets violated here. Then why can we explain this? I will give you that Heisenberg's uncertainty principle answers this question. What Heisenberg's principle says? Heisenberg's principle. Heisenberg's principle says that the uncertainty in energy and uncertainty in time is greater than or equal sum h line by 2. For the for our present case, we can write the approximated value, this approximately equal to some h line. If we take this, then the short interval between the energy exchange becomes equal to some h line by delta E. So if we take the rest mass energy of pi Meson, that h line by m pi c square. Okay. From these, if we consider that the speed of light be equal to the speed of Meson particles, then the maximum distance can be obtained for the Meson particles, as because the maximum speed can be taken as the speed of light. So if we consider the speed of Meson particle be equal to the speed of light, that is the maximum value, then the maximum distance can be occurred by h line by m pi c. This has been observed to be some few Fermi. So the maximum range of the nuclear force can be taken from this equation. This is the Fermi distance that can be covered by the nuclear force. So beyond this level, no nuclear force is present. Only up to certain Fermi, it may be taken to 1.4, 1.2, certain Fermi order, the nuclear force exists. Okay, so from these we can also consider if this can be taken to some few Fermi, then m pi can also be obtained nearly equals some 207 into me, mass of the electron. So this is the mass of the pi mesons. Okay, so I have considered these that pi mesons have finite mass. So the value of the finite mass is can be drawn from this. Now why the photons cannot be taken into account? Because for photon the range which is given by, suppose this is some r, range can be taken to be some mc square. So if we take the mass of photon which is equal to some 0, then this range will be infinity, which is actually observed for Coulombic force. We know that Coulombic force exists for infinite distance, but since it is reciprocal of r square, so the Coulomb force decreases by the increase of distance. But the actual order of the theoretical order of the Coulombic forces ranges is up to infinite. But the nuclear force is range of the nuclear force is some few Fermi, because m pi has some finite mass which is equal to some 207 into mass of the electron, or nearly so. Okay, now Heisenberg's principle says that the energy exchange takes place in a very short interval of time, so that the no change in mass is observed in experiment. This is very short time, so it is hardly to observe the change in mass. Okay, so these are the interesting things which should known to us. Okay, now the next thing is that the Yukawa's model of nuclear force, the mathematical model. Now it is very known to us from relativity that E square is nothing but the p square c square plus m naught square c to the power 4. Here we take m square c to the power 4, where m is the rest mass. So if we convert it into operator form, that is I am actually want to convert it in quantum mechanical problem. So if we apply it in operator form, then we will see that energy operator can be given by I h line del t, and the momentum operator is given by the energy momentum operator is given by minus I h line grad. If I put this operator form in equation suppose 1, then we will see that this is nothing but equal to some minus h line square del 2 del t2 is equal to some h line square uh, minus h line square grad square uh, c square minus c square h line square grad square plus m square c to the power 4. If we arrange them, then h line square del 2 del t2. Okay, let us remove the h line square from um, this, and let us simplify the equation that grad square plus uh, uh, sorry, here the minus, so this should be minus minus 1 upon c square del 2 del t2 uh, is equal some m square c to the power 4 divided by some h line square c square. So c square, this will get c square, so this will become m square c square upon h line square. Okay, now if we take grad square phi minus 1 by c square del 2 phi del t2 is equal m square c square phi upon h line square, and this is taken to the left hand side, then a minus sign will appear here. Just okay, So minus sign appears here and this is taken to be 4 pi gn. Now what is phi here? Phi is the Meson potential. Phi is the Meson potential, and what is Gn? Gn is the Mesonic charge density. Mesonic charge density of the nucleus. Mesonic charge density of the nucleus. And the equation obtained here is known as Klein Gordon Fock equation. Klein Gordon Fock equation, which is very important. And this is purely quantum mechanical concept. Okay. So after knowing the quantum mechanics very well, you will understand better to it, and you get the solution from this equation very well. Now, if we assume the potential to be static in nature, then this term will be vanish, and the equation will be grad square phi minus m square c square upon h line square phi is equal 4 pi gn. So the solution becomes v. If we we take here the phi, so the solution can be taken to be phi is equal nothing but minus gn e to the power minus r upon lambda cut divided by some r, where lambda cut is nothing but h line by m pi c, which is the range, which is nothing but the equal to the range and is known as the Compton wavelength of the Meson particles. Okay, wavelength of Meson particles. Now phi can be taken to be the gn into phi with so if we put the value of phi here from here, then we get gn square e to the power minus r upon lambda cut upon r. This should be equation 3, and this is the actual potential solution. Okay, and the dimension of gn is that of the electric charge, because we know that uh, charge by distance is the potential of the dimension of potential. So gn should have the dimension of charge. Okay, okay, let us then summarize what we have learned from the nuclear force, the different properties of the nuclear force. Summaries, summary of the whole concept. The nuclear force, different properties of the nuclear force. Let us summarize this. Nuclear force is always attractive in nature. Nuclear force is short range in nature. Range is up to some Fermi order. Short range in nature. It is spin dependent. We have shown it by the example of bar magnet. Spin dependent. It is charge independent. Neutron proton, proton proton, neutron neutron are of the same status. These are the four basic properties of the nuclear force, and the model given by the Yukawa is not wholly completed. It is still under modification, so it is a modern topic today and very interesting for research. So thank you very much for watching this. If you like, then please press the thumb button and subscribe the channel for more update. Thank you very much.